surrounded by more rocks, and gas, and a bunch of nothing, mainly. Oh hey, look at that, the rocks are going around the gas. Hold on, what the heck is going on here? To understand, let's look at a little bit of physics. Wait, did I say a little bit? To find out what kind of magic this is, we'll have to go back in time. Okay, not that far. Stop. Yeah, that's perfect. This is Gravity Guy, but most people call him Isaac Newton. One important thing he said is that force equals mass times acceleration. Now, what do all these words even mean? Force is a push or pull on something in a certain direction. Mass tells you how much of something there is, and it's also a measure of inertia, but we'll get to that later. And acceleration is the derivative of velocity with respect to time, but that's too many big words for my taste, so let's just say it's how fast your velocity is changing. The key takeaway is that if you apply a force to a fixed mass, you get a predictable amount of acceleration. If you know all the forces acting on a basketball midair, you can predict with 100% certainty if the ball will go in the hoop or your neighbor's windshield. Whoa, did an apple just fall on my head? Yes, Newton, it did. Yeah, that must have happened for a reason, said Newton, as he discovered that two masses attract one another, making the apple fall. Yes, even you, no matter how ugly you think you are, attract pretty much the whole universe at least a little bit. Hey, can you put that on paper? Yup, said Newton, who gave us the law of universal gravitation. In other words, how much do bodies pull on each other given their mass and distance times a constant. Bigger mass, bigger pull. Bigger distance, smaller pull. Actually, a lot smaller pull. You see, as the distance increases, the force gets smaller by the square. That, my friends, is the inverse square law. Gravity is also the reason why planets in our solar system orbit the sun. They got their initial velocity when the solar system formed out of spinning gas, and since there's nothing in space to stop them from moving, they'll keep moving. Hey, that's Newton's first law. The sun is so massive that the force of gravity keeps pulling the planets towards the sun, but the planets are fast enough to essentially fall towards the sun but miss it, and this goes on forever, creating a round orbit. Actually, that's kind of a lie. Most orbits are not perfectly round, but more egg-shaped, and Pluto's orbit is just a complete mess, but you get the idea. In this case, the gravity is what we call a centripetal force. One thing many people confuse is mass and weight, and no, they're not the same. Mass tells you how much of this blob there is, and weight is the force of gravity the blob would feel. To make things clear, your mass would be the same on the Earth and on the Moon, but the weight you would perceive is different because the Moon has a weaker gravitational pull, meaning a weaker force acting on your mass. So really, you're not overweight, you're just on the wrong planet. Alright, enough about Newton, let's break some stuff. If you it might look like this. What the hell, ground? Why'd you do that? The answer is energy. You know, the thing kids have after eating gummy bears. Energy has the unit joule, and it's not like force. It doesn't have a direction, it's just a number that's kind of chilling there as a property of a thing. You see, there's two main kinds of energy, kinetic energy and potential energy. In plain English, energy of movement and stored energy due to some circumstance. For example, when you held your phone, it stored gravitational potential energy due to being held above the ground at a certain height. Once you dropped it, that potential energy was converted into kinetic energy as the phone fell. Then it smashed into the ground, and the phone absorbed some of the energy, making the screen go boom. Work is defined as force applied over distance. For example, if you lift an apple by 1 meter, you would have done about 1 joule of work. This happened by converting chemical energy stored in your body to gravitational potential energy stored in the apple. As you may have noticed, energy and work have the same unit joule, so they must be the same thing? No, energy is the total amount of work that a thing could possibly do, and work is just the stuff that actually happened and required energy. If you try to lift a weight that's too heavy for you, you'd feel like that took a bunch of work, right? Well, yes, but your feelings are invalid in the face of physics. Mathematically, no work has been done, because work is force applied over distance, and since you didn't move the weight at all, no distance means no work. The key thing to remember about energy is that it cannot be created or destroyed, only converted, aka the conservation of energy. Okay, but a car that's moving has kinetic energy. When the car stops, assuming the car doesn't smash into a wall, where does that energy go? When you apply the brakes, there's friction between the brakes and the wheels, causing the car to slow down and creating heat as a byproduct. That heat is then dissipated into the surrounding air, and that makes the molecules in the air move faster. Things that move have kinetic energy, so ultimately, the kinetic energy is transferred from the car to the air. With this knowledge, we can define that temperature is just the average kinetic energy of atoms in a system. You see, all atoms, not just molecules in the air, wiggle, like this. The faster they move, the hotter things get. That is temperature. All that talk about hot stuff, I think it's time we talk about thermodynamics. It tells us that jumping in lava is probably a bad idea, but more importantly, the absolute mess that is entropy. Literally, it tells you how much disorder there is in a system, indicating the number of possible states a system could be in. For example, get an ice cube, no, not that one, yeah, that's perfect, and put it in the sun. The sun will obliterate the ice cube and turn it into water. Looking at the structure of ice and water, we can see that ice is more neatly organized than water, which just kind of goes all over the place. Also, the water could look like this, or even this, but the ice will always look a little something like this. In total, the system went from low entropy to high entropy, meaning more disorder and more possible microstates. This trend applies to everything. The whole universe is on an unstoppable path to higher entropy. It's also the reason why time seems to only go forwards. Practically, entropy tells us that some forms of energy are more useful for doing work than others. Burn some gasoline and your car will move, spitting out heat and gas. That heat and gas is pretty much gasoline, just in the form of higher entropy. And as you can imagine, this stuff won't really make your car move, and the gas won't spontaneously turn back into liquid gasoline, meaning the form of gasoline with lower entropy is more useful for doing work. Okay, but if you put some water in the freezer, will it not decrease in entropy? Yes, but the fridge is not an isolated system and will heat up the room more than it will cool down the water, increasing the total entropy. Want to see some magic? Whoa, what just happened? Some electrons apparently moved through some wires and let there be light. What is going on here? Objects have a fancy something called a charge. It can be positive or negative, or if you have the same amount of both, an object is neutral. Electrons have a single negative charge. The flow of electrons is called electric current. To describe it, we use three parameters: current, voltage, and resistance. Current is the amount of electrons passing through a wire in a given amount of time. Voltage is what pushes the electrons to move, but simply put, it's a difference in electric potential, so you can imagine it as a slope that goes from high potential to low potential, where the flow of current goes downhill. And resistance is pretty self-explanatory. This is Coulomb's law. Wait a minute, this is just Newton's law of gravitation in disguise. This tells us that electric charges attract each other in a similar way masses do. Opposites want to cuddle, while like charges literally couldn't think of a more disgusting thing than to be with one another. These four equations explain pretty much all of electromagnetism, but don't be scared just because they look scary. I mean, yeah, they do, but it's simpler than it seems at first. The first one states that if there's an electric charge, there will be an electric field, or this big E, emerging from it. Add another and you have an electrostatic field. These lines tell us in which direction a charged particle would feel a force at any given point. The second one tells us the same for magnetic fields, and even though electric charges are cool and can be alone, magnetic poles are not. They're very lonely, and there will always be a north pole together with a south pole, and a single pole can never be alone. Okay, now here's where things get kinda freaky. You know how electric charges only act on other charges and magnets only affect other magnets? Well, that's only true if they're not moving. The third and fourth Maxwell equations tell us that a moving magnet creates an electric field and a moving charge or electric field creates a magnetic field. One consequence of this is that current can seemingly come out of nowhere by moving a magnet next to a conductor. The moving magnet creates an electric field which makes the electrons inside the conductor go crazy. That is called induction. In other words, electric and magnetic fields are so tightly linked that they are two parts of the same bigger thing. Let's say we have a charge. Since it doesn't move, it has a static electric field. If we accelerate the charge, there will be a magnetic field around it. That magnetic field interacts with the electric field, which again changes the magnetic field, and this is a sort of chain reaction that makes the electromagnetic field radiate outwards into space as an electromagnetic wave. Depending on the frequency, the human eye can actually see this. It's called light, but most of the spectrum is invisible to the human eye and is used for things such as Bluetooth, wireless charging, and confusing human apes into thinking magic is real. Hey, can we go back to the water and look at those molecules? Yeah, those. What are they made of? The are made of atoms. Atoms are made of a core and some electrons. The core is made of protons and neutrons, both of which are made of quarks. They're strange yet charming from up top down to the bottom. Oh yeah, there's some more stuff, like for example the overweight brothers of the electron. All of this together makes up the Standard Model, which we believe to be the smallest things in the universe. At least that's the excuse we have for not knowing what quarks are made of. Fun fact, depending on the number of protons in the core, you get different elements. Depending on the number of neutrons in the core, you get different isotopes of the same element, most of which are a little overweight and very unstable, so they fall apart into smaller atoms. That releases ionizing radiation. Not so fun fact, that stuff will kill you. If you have a large group of atoms, you can predict when half of those will have fallen apart. That's the half-life. Depending on how unstable an isotope is, it will survive a certain amount of time. Some don't want to live, some really don't want to live, but some will live far longer than you probably will. Oh yeah, did I mention that light is like the fastest thing in the universe? To be exact, 299,792,400 458 meters per second in a vacuum. That is pretty fast, said everyone. Also, light is a wave, said everyone. Why? If you shoot it through two teeny tiny slits, it creates a fancy pattern due to interference, which is just a wave thing. You see, when two waves cross, they can add up or cancel each other out. These gaps are the spots where they cancel each other out. So in this case, light behaves like a wave. Nah, screw that. Everything you know is wrong, said Albert Einstein, probably smoking crack after hearing about the photoelectric effect and discovering that light comes in tiny packets called photons. I sure hope that doesn't unravel a whole new area of physics. Anyway, he said, as he continued to casually drop an absolute bomb on the entire field of physics with his theory of relativity. He assumed the speed of light is constant because it arises from two other constants. He also assumed the laws of physics are the same for everyone, regardless if moving or at rest. Now think about it. If two people turn on a flashlight, but one person is standing still while the other person is on a moving train, wouldn't the person standing still see the other person's light as going faster than the speed of light? The reality is, no, it would be the same as their own flashlight. That's impossible, except if time passes slower for that person from the perspective of this person. In other words, if the speed of light is constant, time must be relative. Also, gravity is not actually a force, sorry Newton, but rather a consequence of masses bending space-time. Einstein thought the universe is a mesh of space and time, and anything with a mass bends this fabric. Also, all objects move freely on a straight line when moving through space. Gravitation is simply the result of objects following these bent lines which appear straight to them. If you have a hard time understanding this, you can imagine two people on Earth walking in parallel straight lines. Now imagine one standing on the east coast and one on the west coast of the US. If they both walk north, eventually they'll meet at the North Pole. Because of the curvature of the Earth, they ended up at the same point even though they both walked straight relative to themselves. Oh yeah, by the way, energy and mass are kind of the same thing, he added, which explains why atom bombs are so freaking powerful. According to this formula, even just tiny atoms can release a humongous amount of energy by giving up just a fraction of their mass during fission. What is fission? It's the same thing Oppenheimer used to make this thing go boom. You see, there's two main ways to gain energy from changing nuclei, fission and fusion. Fission aims to split the nucleus of an atom into two or more smaller nuclei, which is most often achieved by blasting the core with neutrons. Fusion is the opposite, where you combine two smaller nuclei to get one bigger one. The energy came from something we call a mass defect, where the resulting nucleus is lighter than the starting nuclei. This missing mass is what was converted to energy during fusion. Fission and fusion are cool, but you gotta be careful or you might just blow up the planet. That totally didn't almost happen before. Multiple times. Hey, remember when Einstein said light is a particle? He accidentally discovered a whole new field of physics which he thought is just a giant hoax. Quantum mechanics. This stuff is crazy. Another German guy called Max Planck said, yes, Einstein, you're right. Light does come in tiny packets. Actually, all energy comes in tiny packets, or quanta. Want to know where an electron is inside an atom? It's here. And there, and everywhere at the same time, actually. That's a superposition. It's not in one state, it's in multiple states at once, at least until you measure it. Then it chooses one cozy spot to be in. Schrödinger gave us an equation that gives you a probabilistic model of where you can find it if you were to measure. You can imagine this as a cloud, and the denser it is, the more likely it is for an electron to be there. But still, where exactly it will end up once you measure it is random. Speaking of observing particles, they're also super sensitive about their private data. Look at these two images of a flying ball. In one, you can clearly see where the ball is, but not in which direction it's moving, and in the other, you can see where it's moving and approximately how fast, but not where exactly it is at the moment. That is essentially Heisenberg's uncertainty principle. You can never know both the exact position and the exact speed of a quantum particle at the same time. Okay, let's recap. A small thing can be a particle and a wave at the same time, and when we try to look at them, weird stuff happens. But you know what? It gets even weirder. Think back to the double slit experiment. We know that a light beam acts as a bunch of waves and we get interference. But here's the weird thing. Even if you send individual photons after sending enough of them and detecting where they end up, you get interference. Like, how can that be? What did a single particle interfere with? Well, we think it interfered with itself because it acted as a wave and went through both slits at the same time. That's a superposition. Okay, well, let's just measure which slit it goes through. Yeah, that's not gonna happen. Once you start measuring which slit the photon goes through, it stops acting like a wave and the interference pattern disappears, as every particle chooses just one of the slits to go through. Sounds kinda suspicious to me. Anyways, all this knowledge is going to cost you one subscribe and a thumbs up. Thank you very much. And you can decide if maybe you'd want to tip with a comment, perhaps.